Hey everyone and welcome back to PrepFusion. So this will be the lecture 8 of time domain analysis. So in this lecture I will solve the assignment problems that I gave in the previous lecture. So this question is a gate question. So the question is asking a system with transfer function g of s equals to 1 by s square plus 1 has 0 initial condition. So transfer function has anyway 0 initial condition, doesn't need to tell. The percentage overshoot in its response is this. Okay, so now we have to tell the maximum peak overshoot, right? MPO. So how will you tell this one? So this one is a bit different because the transfer function is this one. So what is my, like, this is not my OLTIF, right? This is my CLTIF. If my CLTIF is this one, so what I can notice here is solution. I will not write g of s, I will write t of s, right? So t of s equals to 1 by s square plus 1, right? So t of s equals to 1 by s square plus 1. Now, right, if my t of s equals to this one, what do I notice? My zeta is 0, right? What is my standard characteristics equation? It is s square plus 2 zeta omega n s plus omega n square. So from here I can notice my zeta is 0. If my zeta is 0, what does this mean? There is no damping. So this is the undamped system. Okay, this is the undamped system. So how does my undamped system look like? Okay, so my undamped system, right? So basically in graph, if you see for a unit step response, it oscillates between 0 to 2, right? Oscillates between 0 to 2. This is my graph, right? I hope you remember. Okay, this one was the first one that we derived, right? I hope you are revising the concept also. So this is for an undamped system. This is my y of t. Okay, this is my t, and this is going from 0 to 2. Okay, like for a step response it is chilling, right? Okay, why did I go? Yeah, for a step response it is chilling. So if for a step response it is chilling, then basically for a step response it will swing between 0 to 2, right? It will swing between 0 to 2. Okay, so yeah, can I calculate the maximum peak overshoot for this one? Okay, but you might ask that how can I calculate, because I don't know the steady state value. So for undamped, what we do, okay, in case of undamped, we assume that my steady state, right, y steady state is equals to average over a cycle, okay, of the output, right? So that is what we assume. Okay, so this is average of y of t over a cycle basically, okay, into dt. Okay, so this we have to assume. Okay, so if this we assume, so what does it mean? So this, what is y of t equals to? So y of t equals to 1 minus cos omega n t, right? So this is my y of t. Now what is omega n? So omega n, from here I can notice that omega n square equals to 1. So omega n equals to 1, right? Omega n equals to 1. Okay, so yeah, this is my omega n. So it is basically equals to 1 minus cos of t, right? 1 minus cos of t. So now I will simply integrate this over a cycle and I will see what is my value. So even like this does not matter, because if I integrate this, right, over a cycle, this will be simply 1 only, and this will be simply 0. This average value of cos t is 0, so I will remain around 1 only. Okay, so yeah, so my y of average, y of steady state of t equals to y of average equals to integration of 1 by 2 pi 0 to 1 minus cos t, right? So this is equals to simply, okay, it's not 0 to 1, sorry, 0 to 2 pi. So it is simply 1 by 2 pi into 2 pi minus 0. Okay, because cos t over a whole cycle, the integration of cos t is 0. So this will be 1 only. So this is basically my y of steady state. Okay, so I will find my maximum peak overshoot for a undamped system like this one. So MPO, percentage MPO but like you can remember this also, like I derived this, but basically the percentage MPO for an undamped system will be 100%, right? Because it will oscillate from here to here totally a one unit, right? That's why. So percentage MPO equals to simply y max of t minus y ss, right? Y ss is y average of t divided by simply y average of t. Okay, so this is my formula for undamped, but this will always be equals to into 100 also. I have to write into 100%. Equals to 100%, right? So this is equals to 1 only, 2 minus 1 divided by 1 is equals to 100%. So this you can remember, for undamped system the percentage MPO will be 100%, right? So this is just a boundary condition. Okay, just a boundary condition. This is valid for a undamped system. Okay, now let's I will also derive it for a critical damped system, right? So for a critical damped system, what will be my percentage MPO? I'm just laughing because something came into mind. Okay, so yeah, me and him actually were discussing something, so yeah, some funny topic came into mind. So what was my expression for a critical damped system? What was the step response? So it was basically y of t equals to 1 minus, I hope you remember, it was 1 minus omega n zeta n omega t, and also minus omega n t e raised to power minus omega n zeta t, right? So this was the basically expression for a step response, right? So how did my graph look? My graph looked something like this one, right? Okay, this is this one, this one. Okay, so my graph is looking something like this one. This is c of t and this is t. Okay, so yeah, this is equals to 1. Okay, so yeah, this is this one. Now basically, right, what is the peak overshoot? So is there any peak? My peak is 1 only, right? This is my peak, right? This is my peak. Okay, now what is basically what do you say, steady state value? Steady state value is also 1. Okay, so like there is no first peak. Basically I have only one peak, that is equals to 1. So y of peak, because there is no oscillation, right? There is no oscillation. Okay, so y of peak equals to 1 only, and y of steady state equals to, what do you say, y of steady state equals to 1 only. So what will my MPO? So percentage MPO simply will be equals to, as there is no overshoot, right? Because critical damp is just perfect damping, there will be no overshoot and it will reach its steady state much faster. So MPO will be minus y steady state divided by y steady state, which is equals to 0, right? Because peak and steady state are same. Okay, so it is equals to 0 only. So this is equals to this one only. So yeah, these two things you have to just keep in mind that there is no like overshoot in critical damping. Okay, also in over damping there is no overshoot, right? So only overshoot is in like undamped, and like it, we can't even call it overshoot because it is always oscillating, right? And we don't know what is the final value, but still we call it, like, assume that the steady state value is that average one over a cycle, and we tell yeah it is overshoot. And for underdamped systems there is overshoot. Okay, but for overdamped and critical damped and for first order system there is no concept of undershoot or overshoot or peak time, something like that. Okay, so yeah, this was basically it for this question. Now let's go to the ninth question. So what does the ninth question tell us? So we have a feedback system shown below. Okay, and the OLTF is shown here with k multiplied with it. So this has is shown. Okay, then the step response of the closed loop system should have minimum settling time and have no overshoot. What would be the required value to k for this to achieve, right? So which damping provides us minimum settling time and no overshoot? So basically we know this, right? Just a few seconds ago I told that critical damping will provide us minimum settling time and it will also give us no overshoot, right? So what will be the required value of k? So the required value of k, right? Required value of k will be simply first we will find the CLTF from OLTF, and then we'll compare this with critical damp system, standard critical damp system. So my CLTF will be equals to OLTF divided by 1 plus OLTF. Okay, so this is simply like this is not simply 1 by s square plus 2s, right? There is also a k term here, so it will be k by s square plus 2s by 1 plus k by s square plus 2s. Okay, so this is what basically my like CLTF is. So if I can tidy this one up, so this will be s square plus 2s plus k. Okay, this is my CLTF. So here what I can see, my like DC gain is one only, and this is my transfer function. So what is the standard condition for critical damp? My zeta will be equals to 1 for critical damp, right? So firstly I should write here, so I told you here, but I should also write here that like for no overshoot and minimum settling time, I should have critical damping. Okay, so this thing you have to keep in mind. So I should have minimum critical damping. Now yeah, so for critical damping, what is the condition? My zeta should be equals to 1 only, right? So if my zeta is equals to 1, then okay, I should write, I was writing this for critical damp. So basically, right, so it was so my 2 zeta omega n is 2 zeta omega n is, so not s, 2 zeta omega n will be equals to this coefficient, right? This coefficient which is equals to 2, right? And zeta is also 2 1. So what will my omega n? Omega n will be equals to 1 only, right? So now what is my omega n square equals to? Omega n square equals to this one, right? K. Okay, so omega n square equals to k, so my omega n will be equals to under root k. Okay, so omega n will be equals to under root k. So now omega n is 1. Okay, or like I have to find the value of k itself. So yeah, omega n is 1, so omega n square will be 1, so k will be equals to 1, so my answer will be 1. Okay, so here my answer will be 1. Okay, and here, like here the answer was 100%. It was for an undamped system, right? That's why it is 100%. It always oscillates. So yeah, for this one I hope you got it, that how I got the k, the standard question only. So now this is a bit good question actually. So we have been given the closed loop transfer function, like we have to determine the closed loop transfer function. We have been given the response of a second order system for a input of 3 ut. So basically we have been given a step response, but the step has a amplitude of 3. So this is the step response for a 3 ut signal, and this is my transfer function, basically system, right? Block diagram. And what is told, this is a second order system. Okay, so concept of damping will come. So like from here only we can understand what type of damping is present. It is underdamped, right? It is underdamped. Why? Because it is oscillating around the steady state value. Okay, so from there you can understand. Also we have to calculate all these parameters. Okay, but before going to this, firstly obviously I have to find damping ratio, damped, and natural frequency. This one I have to find for writing the closed loop transfer function. Okay, first I will try to find this one. Okay, but I have been given only this one. So from here, what information can I get? So whenever you are given graph, just check on the graph, what information can you take out from that? So what information can you take out from the question? Okay, so let me copy this graph. If I copy from this graph, right, so what do I get? So what will be my like peak time? What is my peak time here? So it is given, right, this 3, it has given 3 seconds is reaching 8, so that is my peak. 8 is my peak, and it is reaching my peak at time equals to 3. So my from here I can find my what do you say, my peak, that omega d, right? Because what was my formula for peak time? I hope you have revised. It was pi upon omega d. It was the first peak, right? First peak. So my pp is equals to 3 equals to pi upon omega d. Okay, so from here I can find my value of omega d. So omega d, this is something 3.14 and this is 3. So I've already written the calculations. This is 1.047 radian per second, right? Okay, 4.0 radian per second. Now what is my MPO? MPO, right? MPO percent, I will write not percentage, I will write directly, because that will help me in finding the angle. So MPO formula is, we know, e raised to power minus cot theta. Okay, not in percentage, just simple, which is from here. Can I find the MPO? What I can see? I can see that initial it is settling to 6 and peak value is 8. Okay, and will this matter that I have a 3 UT here? Will this matter? If my step was, let's say, 2 UT, so will my MPO change? Okay, so in the definition of MPO, what I said was it was normalized, right? It was normalized. The AK were cancelling each other out. So that's why there is no AK term here in here, right? A is basically the amplitude of the step and K is the DC, right? So AK are cancelling each other out. So simply, right, I'm getting e raised to power minus pi cot theta, which is independent of my DC gain and the amplitude of the step function. That's why MPO won't matter whatever amplitude of input I am giving and whatever the DC gain of the system is. It is independent of those two things, right? So basically, right, now this will be e raised to minus pi cot theta, which is equals to simply 8 peak value minus the steady state value divided by steady state value. It just normalizes it, right? So what will I get? This is 2 by 6, this is 1 by 3. Okay, so this is 1 by 3. So e raised to power minus pi cot theta equals to 1 by 3. So now what you do, you simply take the log of this one. Okay, you take the log of this one, then you multiply by minus 1, then you divide by pi. Okay, and then you take the inverse. Okay, then you do the tan inverse, and then you find the theta. Okay, that is what you do in gate calculator. So I'm telling you the procedure, right? What you do? Okay, I will write this down. So first you will do is take log on both sides. So you will get minus pi cot theta here, and here ln of 2 by 3. So ln of something less than 1. Okay, not 2 by 3. This is, yeah, this, sorry, this is 1 by 3 actually. Ln of something less than 1 equals to negative only. So what I can do is multiply by minus 1 both sides. This will be cot theta by ln of 3. Okay, you know, right? Minus ln minus of ln of something, it reciprocates, right? So now what is my, I will take this cot theta to here, and this one I will find the value and divide it with pi, right? So I will get some value for cot theta pi by ln 3. Okay, equals to tan theta. Now, like I'm telling you this procedure that you will do in gate calculator, right? So now what you will do, you will do the tan inverse on both sides. So tan inverse button is directly present over there, cot inverse isn't, right? That's why you use tan inverse. So then you take the inverse, so theta equals to tan inverse pi by ln 3. Okay, whatever the value you get. Now from here you get the theta. Now from theta, what you do, you do cos theta, right? So and you find the zeta value. Okay, that is how you do for finding the zeta. Or like what you can do, use the different formula also, but that will be a bit difficult. You have to solve the quadratic equation, right? So that's why sometimes I prefer this one. Okay, sometimes I prefer that one. Okay, so if zeta is given, then I will use this formula. What I am talking about, this one, right? Minus pi zeta upon 1 minus zeta square. Okay, you can use this formula. Okay, But if that one is given, if my angle is given, then I will use the angle formula, okay, or something else, okay. If my MPO is given, then also I can use the angle formula, whatever suits you, okay. So you use the formula according to whatever suits you, okay. So yeah, that one was for that one. Now I just told you the procedure. Now let's actually write the value. So this is my MPO. So 1 by 3 equals to, write it, yeah, e is to minus pi cos theta. So my theta will be simply, I have already written it down. So this is 70.56 degree, okay, already calculated. So now I have to find zeta. So zeta equals to cos 70.56, which is almost equals to 0.33, right. So this is my zeta, right. This is my zeta. So I found the zeta, I found my omega d. What I can do, I can find my omega n also from here, right. So what will be my omega n? This is the, I am doing the 11th one, right. So what will be my omega n? Omega n will be simply equals to, so one formula that I know, what is omega d equals to? Omega d equals to omega n under root 1 minus zeta square. So this is my omega d equals to. So now, right, sorry if my face wasn't visible, okay. So now, right, what will be my omega n? Omega n will be equals to omega d by 1 minus zeta square. Omega n equals to omega d. So what is omega d? Omega d is 1.0047, and zeta is basically 0.33. So this is 1 minus 0.33 whole square, okay. So like I have already calculated this one. So this one will come out to be somewhere around 1.11 radian per second, okay. So this will be my value for the sorry, not 1.1 was, okay, did I do something wrong? Okay, sorry, I think I've written something wrong over here. No, sorry. So it was 1.11 radian per second only. Maybe I calculated something, sorry. So yeah, this was 1.11 radian per second. Now what else is left for us to find the transfer function? So we know omega n, we know all these things, but one thing we don't know. What do we know? So I can write my transfer function as this one, right, that omega n square, this one 1.11 square divided by a square plus 2, zeta is 0.333, omega n is 1.11 plus omega n square, okay. So this is my transfer function basically, okay. This is my transfer function. So now, right, now is this the correct answer? This is not the correct answer, right? So why? Because I have a DC gain also. I have to find whether my DC gain is 1 or not 1, because my steady state value is 6 and I am applying a 3 amplitude of step, so there must be some DC gain, right? Else my steady state value also would have been 3 only, right? So what is my y of infinity equals to? My y of infinity equals to ak, right? I will remember, right, that formula, that ak into 1 minus e raised to 1 minus omega t, that sign. So it is equals to ak. So this one is equals to simply a is what? A is 3, right, the amplitude of the step. And what is k? K I know, don't know. K I need to find, because k will come over here, right? K will come over here, right? And this is equals to my 6 only. Steady state value is equals to my 6 only, okay. So what is my k equals to? K equals to 2, right? DC gain equals 2. So now what will my complete transfer function? Basically my complete transfer function will be copy and paste and also a 2 multiplied with it, right? So there will be a 2 also. So this will be my actual transfer function, okay. I am not calculating it, okay, not that important, but this will be my answer for the 10th one, okay. And previously I was solving the 11th one. Now let's solve for the other parameters. As we know, zeta, theta, all those things we know right now. Okay, so what do we need to find out next? So next we need to find the decay. Okay, I think I have written it down. This will be decay ratio basically. Sorry, like this will not be decay time because delay time is already found out. So this is decay ratio. Okay, now what is decay ratio? So basically, right, if I copy this one, okay, so what do you mean by decay? Decay means it is reducing, right? It is reducing. Now this is also another term, parameter, so this you should keep in mind. So what do you mean by decay ratio, right? So decay ratio, this one is the 12th question. So what is decay ratio? So decay ratio, right, decay ratio is simply that this is decaying, right? My peak is decaying. Okay, I can't say about undershoot because undershoot is also decaying but in the opposite direction, so that is not the correct way of like representing this. So what I can represent is my peak is reducing, so from first peak it is reducing to this peak, right? So basically, right, basically it is the ratio of the second peak to the first peak. So it is basically equals to my MPO1 MPO2 divided by MPO1, right? So yeah, this formula you have to you don't have to remember, you can also understand, right? Decay means it is decaying, so my peak is decaying, that's why it's the first like the second peak divided by the first peak. So this is basically my peak, right? So what is this equals to? Okay, I can expand this also. We know the standard formula, right? So my second peak is what? It is e raised to power, like when does it happen? N equals to odd, right? N equals to 3. Okay, n equals to 2 the undershoot happens, and at n equals to 3 the overshoot happens, like the second overshoot, right? So it is e raised to power minus 3 pi cot theta. Okay, and this is equals to e raised to power minus pi cot theta, right? E raised to power minus pi cot theta. Okay, so now like I can write this in standard format. What is it equals to? E raised to power minus 2 pi cot theta. Okay, so this is my like this is standard formula. You can remember this also, or you can derive this also. Deriving this will take only 1 second, right? So or you can remember it will be e raised to power minus 2 pi cot theta. Okay, so yeah, directly put that. So what we know e raised to power minus pi cot theta equals to 0.33, right? So was it really? No, it was, yeah, it was 0.33 only, because 1 by 3 only. Okay, so it was 0.33 only. Now what will be my e raised to power minus 2 pi cot theta? It will be simply square, right? If I square this one, okay, if I square this one basically, then I will get my desired answer. So which is equals to, simply I have already written down, it is 111, like 0.111. So that is basically my what do you say, that is basically my decay ratio. Okay, that is my decay ratio. Now let's find the other parameters. So other parameters are like simply time domain only, which is what one was the 13th one? It was the, okay, maximum peak overshoot. I've already found it out. Okay, I think here, yeah, maximum peak overshoot, already got it. Okay, in percentage, okay, MPO percentage is 33%, right? Because 1 by 3 times 100 is equals to 33%. Okay, so this is equal to 33%. So yeah, the MPO I've already found out. Now I have to find the rise time. So rise time is 14th one. Okay, rise time is 14th one. So if my rise time is 14th one, so TR, what was the formula of TR? So I hope you remember, right? What we should do was sine omega dt plus theta was equals to 0. Okay, as it reached is one value. First time it reached to its 100% value. So then we found out that sine that will be equals to pi. So this is pi minus omega by pi minus theta by omega d. So I will just put pi minus what was my theta was 70. What was theta? Theta was 70.56, right? So it put just theta 70.56 by what was omega d? Omega d was I think yeah, it was 1.047, right? So 1.047, and you will see that I'm getting some weird bizarre answer. Why? Because this, right, this is in degrees and this is in radians. This is also in radians per second. Okay, so all these are in radians. Okay, but this is in degrees. So what you have to do? You have to convert this into radians. Okay, so what do you know how to convert a degree into radian? If you forget it, just simply, what do you know, like pi radians? Okay, or 180 degree equals to pi radians, that we know, right? Half circle is 180 degrees and that is equals to pi. Now what will be equals to my 1 degree? 1 degree will be equals to pi by 180 degree, right? That will be my 1 degree. Now I need 70.36. Simply I will do the scaling method. So I will multiply this by 70.36. So simply here I will multiply by pi by 180, right? So yeah, that's how you do, remember, right? So now if I like solve this one, I've already solved this one. So like it will come out to be something 1.823 seconds. Okay, my rise time will come out to be 1.823 seconds. So this is my rise time. Now what is my what was my 15th okay, it was, yeah, delay time, right? Delay time is again that what was this was simply that formula, right, that I told you to remember that time. Sorry, okay, you have to remember that one. Okay, it is basically time it reached to 50%. You can cross verify that it is less than the rise time, right? From that you can cross verify. So delay time is basically 1 plus 0.7 zeta by omega n. Just remember that here omega n will come, here omega d will come. Okay, like that you can differentiate, right? Here theta will come, here zeta will come. Okay, so yeah, now what do you do? This is 1 plus 0.7 into 0.333, right, divided by omega n. Now what is omega n? Omega n is equals to simply we just found out, right? What was omega n? It was, yeah, 1.11, right? It was 1.11. So here I will put 1.11 again. What was the result? It is like almost equals to 1.1109 seconds. Okay, almost equals to 1.1109 seconds. Yeah, this one, yeah. So yeah, this is my delay time basically. Now let's find the settling time. So what was my settling time? Which one is it? This one is the last, is it? No. Okay. Oh, the question is itself different because we have to find the number of periods before it settles within 2% interval. What does this mean? So let me take the graph again. Okay, so if I take the graph again, right, so we have to find the number of periods within which it settles, right? Okay, I mean within which it settles. What do you mean by periods? Basically this cycle, right, whatever it is doing, as I told you, right, in previously also I told you that what is one time period? One time period is pi by omega t, right? That is one time period. So but it is now telling us to find how many number of periods are there. Basically what it is telling us to find is basically the number of cycles. So this is 16 one, and number of cycles it reaches steady state. Okay, until it reaches steady state. Okay, so this is basically my like definition for NO. Okay, definition for NO. So NO is this one. Okay, so basically so what will be NO equals to? NO will be equals to simply what is like in one cycle how much like does it how much time does it take. So basically, right, one cycle is basically this one, right? So this one is my from one peak to another peak, right? This one is my one cycle. So this is basically 2 pi by omega d. Okay, this is my one cycle that I complete one cycle. Okay, so but how many cycles do I need to cover? So let's say I cover this much seconds, right? One cycle is equals to this one. Let's say my settling time is like settling time is t settling, right? T settling. So for this amount of time, how many cycles will I cover? Simply what will be for one cycle? Okay, let me write this in different manner. So NO will be for t settling, and for one cycle I am covering 2 pi by omega d. Okay, so what I will do, I can simply take the ratios, right? So I can simply take NO by this because these are proportional to each other. So NO by 1 equals to t settling by 2 pi by omega d, or like this one you can also understand this is for one cycle time period. Okay, and I need the I get the total time. So total time by one time period will give me the number of periods, right? So this is my NO. Like that also you can understand. So my NO will be equals to t settling by 2 pi by omega d. Okay, yeah, this is basically my NO equals to. So what is my t settling again, right? T settling, you remember the formula, 2% error band it has told. So my t settling equals to 4 tau, right? Not 3 tau. And what is my tau? Tau is g tau omega, 1 by g tau omega. So it will be so 4 by g tau omega. So zeta is basically zeta was what? Okay, and again go back there. So zeta was if I can find 0.33, right? And omega was 1.11, I think, or it wasn't. Omega n was 1.1, yeah, 0.33 into 1.11. So 0.33 into 1.11. Okay, so this is basically my zeta omega. So what do I get the result? So my t settling rate is 10.92 seconds. Okay, already calculated this one. So this is t settling. Okay, so now right now let's find this for like NO, right? How many number of cycles does it cover? So NO will be equals to simply t settling by one time period. Okay, one peak time. So one peak time is what? This one only, right? Okay, like this is pi by omega d. So what will be 2 pi by omega d? So 2 pi by omega d will be simply equals to 6, because what we know, like pi by omega d, we know that is the peak time, right? Pi by omega d equals to 3 and 2 pi by omega d equals to 6. So this is equals to 6. So what will be my NO? NO will be equals to 1.82. Okay, so this is basically my number of cycles. So I have solved this question totally. Okay, so this will be basically it for this lecture, and the next lecture we will be doing the parameter analysis of second order underdamped system when the poles are varying, right? Yeah, thank you for watching.